Good morning, student. This is the 11th lecture of your transport phenomena subjects, where we are going to start with something new. Okay. So far, we have seen is that using a simplified shell momentum balance, it is possible to account for all the forces acting on the different surfaces of the shell, and we can express the convective momentum that comes into the system. Okay, so that is the conductive momentum. So in other words, the molecular transport of momentum or the shear stress which is acting on the lateral surfaces of the control volume. So we have also identified the forces which can act on such a control volume would be the surface forces and the body forces. And we have seen the pressure forces is the only surface force and the gravity as the body force. Now if the system is at steady state, then we understand that the sum total of all these, that is the rate of momentum in by two different mechanism minus rate of momentum out plus sum of all forces acting on the system, must be 0 now in order to maintain it as a steady state. So these give us different situations where the smaller dimension is allowed to approach 0. So few examples we have discussed in the earlier classes, in the earlier lectures, where we have solved few problems. Okay, so in every case we are taking a control volume of the shell for the different situations and where the smaller dimension is allowed to approach 0. So in other words, we have used the definition of the first derivative when, let's say, del x tends to 0. Okay, del x tends to 0. So the definition of the first derivative would give us rise to a differential equation too. So the differential equation describes the laminar motion of the fluid layers, that is the slipping past one another. So it is a steady state and there is no unbalanced force acting on the system. Now for example, in the case of flow through a vertical tube on the application of pressure differences and the gravity, the velocity was a function of radius, but it was not a function of axial distance, which is z. So velocity at a fixed r location and the velocity at some other of z direction at the same r location. So these two velocities are same. So the velocity does not vary axially, it's only vary radially. For the case of flow through a vertical tube, flow through a vertical tube, the velocity does not vary axially, it only varies radially. So and we have also found that the velocity distribution was parabolic in nature and the maximum at the center line, and from the expression of the velocity we got the parameter of interest. In the case at every point in the flow domain we could differentiate the velocity profile, and if this is a Newton fluid, then we understand the shear stress is simply the point to be a shear stress which is equals to minus mu multiply with that the velocity gradient at some specific value of r, where the r is the radius of the tube. So with this approach we did find what is the shear stress exerted by the fluid on the walls of the tube. So what are the wall shear stress exerted by the fluid on the walls of the tube, and we also derived which will be able to find the formula of the average velocity. This is the axial average velocity across on the area which is perpendicular to the direction of flow. So it is the cross section of the tube across where we average where we got the average velocity, where we have obtained an expression of the average velocity. So this average velocity profile multiplied by the area would give us the volumetric flow rate, that is also well known as the Hagen-Poiseuille equation. So there are some few other examples that we have solved in the previous classes, and the flow along an inclined plate, or the flow along the outer wall of the tube, where the flow comes from below and comes to the top of the tube and spills over and starts to flow down outer side walls of the tube. Now progressively what we have seen is that the approach that we have used so far is appropriate for simple systems where the flow is one dimensional, laminar, steady, and the geometry is straightforward. Okay, so we are more appropriate for simple system where the flow is one dimensional, laminar flow, steady, and the geometry is straightforward, very simple geometry. So we have increasingly felt that the need of formalize our treatment of transport through any system, even it at steady state case. So in order to do that, one must first start with some two or three basic definitions of how do we define the derivatives of a system in the class. So I will talk about what is going to be the partial time derivative, the total time derivative, and the substantial time derivative. Okay, so in order to do that, first we need to start with some two or three basic definitions of how we define the derivatives of a system, and we will talk what is the partial time derivative, total time derivative, and the substantial time derivative. So these are few important concepts which must clarified before we get into the next part, which is the simple continuity equation. Okay, which is the simple continuity equation. So I will talk about the entire derivation, and then we will go in the equation of motion of a special form of equation of motion of a fluid, which is known as the Navier-Stokes equation. Okay, now once we have the Navier-Stokes equation with us, then we would see that all the problems we have handled so far can be handled very easily by choosing the appropriate Navier-Stokes equation for the flow situation. And once that is done, we will solve a few more involved problems. Okay, now we will start the topic of our today's lecture, the equation of change for isothermal systems. Now when we talk about the equation of change, there are certain definitions which need to be clarified. So you are trying to measure something as a function of time, and depending on where you are, what are you doing, and the values of the quantity that you measure as a function of time can greatly vary. Okay, so what we are trying to measure something as a function of time, and depending on where we are and what we are doing and the values of the quantity we are measuring as a function of time. So I will try to give you an example so that you can clear understanding of these different derivatives. Now let's consider here we can see uh, that you pick a busiest intersection of some place in your college campus. Okay, let's consider you pick the busiest interaction of some places in your college campus where roads have come from all sides at the crossing. So now you are standing right. So you are standing right at the center of the intersection, and you have been told that to count the number of people who are wearing a yellow shirt. Okay, so this is you are standing at the intersection of all the roads, and you are uh, you have been told that to count the number of people who were wearing a yellow shirt. So you are standing at the middle of a crossing and counting people who were wearing yellow shirt. Now you are static at the point. So you are in static at this point, and you are measuring the number of such people as a function of time. So every second you are trying to see how many yellow shirts you can see, how many yellow shirts you can see. Okay, so every point you are measuring the number of such people as a function of time, and who is wearing a yellow shirt and how many peoples are wearing the yellow shirt, and we can see while you are stuck at a position. So you are at the center of the reference frame, which is static. So you are in the center of the position which is in static. Now, so you are, as you are the center of the frame which is static, and any quantity that you are measured as a function of time the is known as the partial time derivative. Okay, so every every second that you are trying to see how many yellow shirts you can see while you are stuck at this position. Okay, so you are at the center of the reference frame which is static, and the quantity what you measure as a function of time, that is known as the partial time derivative, and which is expressed by del c by del t. Okay, which is expressed by del c upon del t, where the c denotes the number of persons who are wearing a yellow shirt. Now, the variation of that with respect to time, where x, y, z are constants, where the x, y, and z are constants. So you are right at the center of the intersection and measuring what is the value of c. Now, while standing there for some time, you are definitely bound to get bored, and you have decided that you are not going to be at the intersection for a long time. So you need to walk around a bit in the area where you are trying to count that the number of persons with a yellow shirt. So you start to move around. Okay, now you start to move around. So your position is not are in the static in the previous case. Okay, now as you are moving around, while you're standing means while you're trying to count the number of the persons when you are moving around, so you have a velocity of your own. Now you have the velocity of your own. Now you can go in any direction that you want with some velocity. Now you still being a very conscious walker, counting the number of persons with a yellow shirt. But since now you have a velocity of your own, the numbers that you are would definitely be different. So the numbers that you are counting would definitely be different, and you had been hit to the place where x, y, z are constants. So you had been hit to the place where x, y, z are constants. So if you measure the number of people while standing at the intersection, and if you measure the number of people while you start to move around with a velocity of your own, these two numbers must be different. Okay, so if you measure the number of people while you start to move around with a velocity of your own, so these two numbers must be different. So when you measure the variation of the numbers of people wearing the yellow shirt as a function of time while you have a velocity of your own, so by definition it is known as the total time derivative, which is denoted by dc dt. Total time derivative, which is denoted by dc upon dt. Okay, now this dc upon dt is simply expressed as dc dt is equals to del c del t plus del c del x multiply with dx dt plus del c del y multiply with dy dt plus del c del z multiply with dz dt. Okay, where this dx dt, dy dt, dz dt are the components of your velocity, because this a you are moving, you are as you are moving around, so x y z are varying with time. So now this dx dt, dy dt, dz dt are the components of your velocity. So obviously this velocity of that you will have impact on the numbers that you count, and that is why it is called the total time derivative, or which is expressed as dc dt. Okay, so as this velocity you will have an impact on the numbers that you count, that is why it is called the total time derivative, and is expressed as dc upon dt. So the next one is just an extension of the previous one. How long you can stand, how long you can stand, so you decided to move with a velocity. So how long you can move around, at some point of time you get tired, and being a busy uh, intersection, there is a lot of crowd which is going in all possible direction. So at some point of time you have decided that I had enough, let's I will simply float with the crowd, no matter which way the maximum number of people are moving. I will move with them with their average velocity, and I will always move with the velocity of prevailing crowd at the point of time. Okay, now but you are still counting the number of persons who are wearing the yellow shirt. Okay, whenever means you are find yourself that you will move with the crowd with their average velocity. Okay, so it the velocity of the prevailing crowd at the same point of time, it always move, but you are still counting the number of persons who are having that yellow shirt, who are wearing the yellow shirt. So now you do not have the velocity of your own. Whatever be the local fluid velocity or the local people velocity, that is the velocity of the reference frame, and the numbers that you are counting in some sort of time derivative of the number of persons, where the reference frame moves with the fluid with its average velocity, or it can also be said that it is a derivative following the motion. So this is generally called as substantial time derivative. So this is called as substantial time derivative. So this substantial derivative is denoted by this capital DC upon capital DT. Okay, so it is derivative following the motion of the fluid, and it is expressed as this del C del T plus Vx del C del x plus Vy del C del y plus Vz into del C del z. Okay, where here this Vx, Vy and Vz are the are the velocities where these Vx, Vy, Vz are the velocities of the fluid surrounding you, or the velocities of those peoples who were surrounding you. Okay, so you let go yourself and float with the fluid, and the numbers that you cannot that your count are known as the substantial time derivative, or the derivative following the motion. Okay, or that is a substantial derivative or the derivative following the motion, because your x y z are varying. So the concepts are important in our subsequent development, where we found what is a partial time derivative, where this stationary frame is fixed, and the total time derivative, where the reference frame has a velocity of its own, and the substantial time derivative, where the reference frame has the velocity as that of fluid. So the substantial derivative, where the reference frame has the velocity as that of fluid. Now we are in a position to derive what is going to be the equation of continuity, as equation of continuity is nothing but a statement of conservation of mass. So this equation of continuity is nothing but a statement of conservation of mass. So if we define a control volume in space, fixed space, and allow fluid to come in and go out through all possible phases, then the rate of mass of fluid coming in minus the rate of fluid that is going out, that will be equals to the rate of accumulation of the mass inside that control volume. So this is nothing but the statement of conservation of mass, and we are going to derive it by the equation of continuity for a system with a Cartesian coordinate system, and the dimensions of the volume is simply going to be del x, del y, and del z. So it is a box where the dimensions are del x, del y, del z. So it's placed in a flow. The liquid is coming in through the x phase, y phase, z phase, and through the phase x plus del y, y plus del y, z plus del y, and the fluid leaves the control volume, and as a result of this there going to be some amount of mass accumulation if possible within the system. So we are going to write the balance equation of such system and derive the equation of continuity. So whenever we have that this control volume, and when we consider that this continuity equation, which is nothing but the statement of the conservation of mass, now as we are defining that the control volume in space with a fixed space, where we allow the flow to come in and go out through all the possible phases, through all these possible phases. Now here we have this control volume, these are the phases, these are the left faces, right faces, top faces, bottom faces, and these are the two faces of this control volume. So if we are allowed to fluid to come in and go out through all the possible phases, then the rate of uh, means the mass that is rate of mass of the fluid that is coming in, that the control volume, minus the rate of mass of the fluid that is going out, this is the control volume, which is equals to the rate of accumulation of the mass inside the control volume. Okay, now we are going to derive it the equation of the this equation of continuity for a system with a Cartesian coordinate system, and this dimension of the system uh, is simply going to be the del x, del y, and del z. So this is the box whose dimensions are del x, del y, del z. So it is placed in a flow, and the fluid is coming in through the x phase, through this x phase, y phase, and z phase. Okay, x phase, y phase, and z phase, and through the phases x plus del x, x plus y plus del y, and z plus del z. So the fluid leaves the control volume. So the fluid leaves the control volume from x plus del x, y plus del y, or z plus del z. So as a result of these, there is going to be some of the mass accumulation. Okay, so there is going to be a mass accumulation. Now in order to derive the equation of continuity, the way we are going to start it, we define the coordinate system. So we define the coordinate system where this is the x, this is the x coordinate, y coordinate, y, and the z coordinate. Okay, so in order to derive the equation of continuity, the way we are going to start, we define the coordinate system x, y, z, and we have this control volume, the which are having the area is del x, del y, and del z, which are having this del x, del y, and del z. Okay, now this control volume, we are taking this control volume as a in a Cartesian coordinate, where we define the coordinate system xyz, and this control volume having the area which is del x into del y into del z. Okay, so the amount of mass is coming in here through the x phase. Okay, so the amount of mass is coming here through the x phase. Okay, through this x phase, which is defined as the phase where the area is del y del z, where the area is del y del z, this area we are considering. Okay, so the x phase is defined as the phase where it has the area del y del z. Okay, del y del z. So similarly this phase whose area is del x del z, del x del z, these areas. Okay, so del x del z so is known as the y phase. Okay, so is known as the y phase, which are having the area del x del z is known as the y phase. And also we have y plus delta y phase, y plus delta y phase. Okay, so this is y phase y, and this one is y plus delta y. Okay, and this one is z, and this one is z plus del z. Okay, now this z phase having the area del x del y, so this z phase having the area del x and del y, which is this area del x del y. Okay, now we are going to write the amount of mass which comes in through all these phases. Through all these phases means the x phases, the y phases, and the z phases. Okay, so the rate of mass in through the x phase. Okay, the rate of mass which is in the x phase can simply be obtained as rho into vx, the density multiply with that the velocity vx at x into del y del z. So this one is the del y del z. Okay, this area is the del y del z, means that the x phase, the rate of mass which is flow in through the x phase can simply be obtained the rho vx into del y into del z, which are having the unit kg per second, which are having the unit the kg per second. So here we are considering the fluid element of volume x y z through which a fluid is flowing. Now rho, what is the rho? Rho here the density of the fluid, and vx vy vz are the velocity component in the x y and z direction. Okay, so mass of entering at x, this is the left side of this control volume from where the mass of the fluid entering at x phase, and this is the x plus delta x, the right phase of this control volume from where the mass of fluid is leaving. So similarly for the y phase also we are having the mass of the fluid which is entering and the mass of fluid which is going out, and for the z phase also we are having the mass of fluid in and the mass of fluid out for the z plus del z also. Okay, now as I've discussed that in the x phase we have the uh, with the mass which is coming in, that is rho vx at x direction multiply with the del y del z, means this area. Okay, which are having the unit kg per second. So this quantity gives us the time rate of mass in through this x phase and the rate of mass out through the this right phase, which is rho Vx at x plus delta x, multiply with this del y del z, the area, which are also having the same unit kg per second. So rho Vx is the mass flux. Rho Vx, this rho Vx is the mass flux which are having unit kg per meter square second. Kg per meter square second. So this mass flux, when multiplied by the corresponding area, we would get the kg per second, or the rate of mass coming in to the control volume, or the rate of mass coming out from that control volume. So as a result, we are going to have 3 in terms and 3 out terms. Okay, so 3 in terms at x, y and z phase. X, y, y and z phase. Okay, so out are going to be x plus del x, y plus del y, y plus del y. So these are the phases. These are the phases, y plus delta y, and this is from the bottom z phase, and this one is a z plus del z phase. Okay, so these would some amount of accumulation, so there would be some amount of accumulation inside this control volume. So governing equation for this case, that will be the rate of mass accumulation inside this control volume, the rate of mass accumulation inside this control volume, which is equals to rate of mass in, rate of mass in and rate of mass out. Okay, so rate of mass out. Now what is the rate of mass accumulation? So now in order to have the mass circulation inside the system, the density of it must change. Okay, so in order to have mass circulation inside this control volume or inside this shell or the system, the density of it must change. So this del rho del T is the change in density of the fluid. So del rho del T, del rho del T is the change in density of the fluid contained within the control volume. So the change in density of this fluid contained within that control volume will be del rho del T. Okay, the now the unit of del rho del T will be kg per meter cube second. Kg per meter cube second. So this must be multiplied with that the volume, which is del x, del y and del z. Okay, so this del rho del T must be multiplied with del x, del y, del z. So to make it kg per second, to make it kg per second. So here we can see that the mass balance means over the element x, y, z, as I have discussed in that control volume, the rate of mass in for the x phase we are considering here, rho Vx at x del y del z minus rho Vx at x plus del x del y del z equals to the accumulation term, which is the rate of increase in mass, which is also the volume rate of change of density, which is equals to this del rho del T, del rho del T multiplied with this del x del y del z, which are also having the unit, to make the unit the kg per second. Okay, as we have the unit for del rho del T kg per meter cube second, and we have the volume del x del y del z, so which is in meter cube. So this del x del y del z multiply with del rho del T, we have this kg per second. So therefore this del rho del T del x del y del z gives us the the time rate of mass accumulation, the time rate of mass accumulation inside the control volume, inside the control volume. So similar expression for the mass entering and leaving in y and z direction we can get. So mass balance becomes, as we have discussed, okay, as we have discussed, this is the x phase through which this mass is flow in and the mass is flow out, and through the y phase, means through this area, del x del z, okay, del x del z, this area we are having the at y phase mass in and the y plus delta mass out, and at the del x means from this bottom area, okay, the at z phase we are having the mass flow in, and at z plus del z we are having the mass flow out. Okay, so as we have the x phase mass balance equation, similarly we can get the mass balance equations for the y and z directions. So the mass balance becomes del x del y del z multiply with the del rho del t, which are having the unit kg per second, which is equals to rho vx at x minus rho vx at x plus del x, which is multiplied with the del y del z, the area, plus for the y phase rho vy minus rho vy at y plus delta y, which are having the area del x del z, which are having the area that del x and del z, this area for the y phase. Okay, so there is some mass going in and the mass going out from this phase. Okay, so del x del z for the y phase, and for similarly the for the z direction, or the for z phase we are having rho vz at z minus rho vz at z plus del z multiplied with that area del x del y, which is this area del x, this is the del x and this is the del y, this area we are considering from the bottom and from the top of this control volume. So this is my overall mass balance of this control volume. Now dividing the both side of this mass balance equations, okay, so dividing these uh, equations of this equation in both side by x y z, and taking the limit as del x tends to 0, uh, it will be dividing by both side by the del x del y and del z. It should be del x del y del z, and taking the limit as del x tends to 0, del y tends to 0 and del z tends to 0. So the equation will become del rho del t, which is equals to minus del rho vx upon del x plus del rho vy upon del y plus del rho vz upon del z, which is the rate of change in fluid that is described over this equation. Rate of change in fluid density described in this equation. Okay, so now we didn't take the this density outside because we did not yet put the special coordinate that the flow is in the special condition, that is the flow is incompressible. Okay, so if I'm allowing the flow to be both either compressible or incompressible, now this expression can be expressed in more compact form, which is del rho del t, which is the here the del rho del t is equals to minus gradient of rho into v, the divergence of rho into v. Okay, so here this rho is in kg per meter cube and v is having the unit meter per second. So this is essentially kg per meter square second, which is the mass flux, and that is a vector, the mass flux, that is a vector. So this is the divergence of mass flux vector, and that must be equal to the time rate of change of density inside the control volume. So this is the time rate of change of density inside the control volume. So that is the one way of expressing the equation of continuity or the conservation of mass. Okay, equation of continuity or the conservation of mass. So if you can expand this term, del rho del t is equals to minus del rho vx del x plus del rho vy del y plus del rho vz del z. So if we expand this equation of continuity, we can have that del rho del t, which will be equals to minus vx del rho del t plus rho del vx del x plus vy del rho del y plus rho del vy del y plus vz del rho del z plus rho del vz del z by expanding this derivative. So after expanding this continuity equation, so we can get that vx multiplied with the del rho del x and vy multiplied with del rho del y and then vz del rho del z. Okay, so it would simply be del rho del t plus vx del rho del x plus vy del rho del y plus vz del rho del z, which is equals to minus rho del vz del x plus del vy del y plus del vz del z. Okay, so it is nothing but what we are what we have uh, described earlier, that that is the substantial time derivative. Okay, so if we expand this term, we have, if we expand this right hand term, we have minus vx del rho del x, plus rho del vx del x. Then for this term vx del rho del y plus rho del vx del y, plus for this term del rho del z plus vz del rho del z. Okay, now this vx del rho del x plus vy del rho del y and vz del rho del z we have. Now if we take those terms in the left hand side with this del rho del t, then we have del rho del t plus all this vx del rho del x plus vy del rho del y plus vz del rho del z, which will be equals to minus this rho del vz del vx del x plus del vy del y plus del vz del z. Okay, so this left hand side, that the term that we have, that del rho del t plus vx del rho del x plus vy del rho del y plus vz del rho del z, which is similar to that substantial time derivative, where we have mentioned this is the substantial time derivative, where we have for the equation of continuity that del rho del t, instead of c we have that the density term del rho del t plus vx del rho del x plus vy del rho del y plus vz del rho del z. Okay, so this is the substantial derivative term, and means if we expand this quantity expression by this substantial derivative, we have the term, instead of this del rho del t, we have the term the substantial derivative, which is capital D rho upon capital dt, which is equals to minus rho divergence of v minus rho multiply with the divergence of v. Okay, in the substantial derivative form. So in another form of the equation of the continuity, where rho is expressed in substantial derivative form, so the two common forms that we would get for the case of equation of continuity, one is del rho del t. Del rho del t is equals to minus rho, means this divergence of rho into v. So this is a vector notation, the divergence of mass velocity vector of rho v, and rho changes with respect to space and time. Okay, so this changes with respect to time. Now, so this is the continuity equation del rho del t. Now we are expanding this. We have, as I discussed, del rho del t plus vx del rho. This is the substantial derivative term, which we can write it as d capital D rho capital dt, which is the substantial derivative form, which can be written here minus rho divergence of velocity. Okay, so here this ddt, the left hand side, is a substantial derivative. Now if we consider it as a incompressible fluid, okay, so if we consider this as an incompressible fluid, is the one in where the densities remains constant. So the incompressible fluid where the densities remains constant, so it is not a function of x, y or z for the incompressible fluid. So if the density is constant for the incompressible fluid, then we'll look at the expression, this substantial derivative term d rho dt equals to minus rho divergence of velocity gradient. It would give us only this term, the divergence of velocity, which will be equals to 0. So which will be equals to 0 if for the incompressible fluid the density is constant. So we have this divergence of velocity will be 0. So another way we can write the divergence of velocity, which is del vx del x plus del vy del y plus del vz del z, which is equals to 0, which is equals to 0. Okay, so this is the form of continuity equation for incompressible fluid. Okay, so the this is the form of continuity equation for incompressible fluid where the density is constant. Okay, so this is the continuity equation, and this is the way by which we can derive the continuity equation from the control volume, where from this control volume all the phases there is a mass of fluid in and the mass of fluid out through the x phase, y phase and the z phase, which are having also the volume, which is del x, del y and del z, which are having the volume del x, del y, del z. Okay, now we are considering the mass balance. We got these accumulation terms, which is in kg per second. Del x, del y, del z is the del rho del t for the x phase mass balance, and for the y phase, this is for the x phase, and this is for the y phase, and this is for the z phase. Okay, so for the x phase we are having the area del x del z, and for the y phase we are having the area del x del z, and for the z phase we are having the area del x del y. Okay, so from this we have got the mass balance equation, and then after simplifying it we have this del rho del t, which is equals to minus del uh, rho vx del x, del rho vx del x plus del rho vy del y plus del rho vz del z. Okay, now this here, instead of x y z, it would be dividing by both side by del x del y and del z. Okay, dividing by both side by del x del y del z, and taking the limit at del x tends to 0, del y tends to 0 and del z tends to 0, we can get this equation of continuity. Now by expanding this equation of continuity, we have this term where we can see, so this is similar to that the substantial derivative term. So this we can write in this form, the substantial derivative form, which is d rho dt, which is equals to minus rho divergence of v. Okay, so in the incompressible fluid where the density is constant, and for this density, constant density, we have the divergence of velocity, which is equals to 0, and from that we have this continuity equation, which is del vx del x plus del vy del y plus del vz del z, which is equals to 0. So this is the equation of continuity, and the next class we will derive the equation of motion. Okay, so next class we will derive the equation of motion. So once we have this equation of continuity and the equation of motion clear, in our mind, we would be able to solve any problem of momentum transfer, as we have described all these momentum balance problems earlier, without taking the Navier-Stokes equations or the continuity equation. uh, so uh, all those numericals will be more easier by considering the Navier-Stokes or the continuity equations in each case. So later on we will describe all these numericals by considering the equation of continuity and the Navier-Stokes equations. Okay, thank you students for this class.